So just to recap, we've got three reference coordinate systems. We can either have the surface of the solid Earth, okay, just as it is, meaning that we have the highly irregular shape that has the shape of the topography, mountains, valleys, as well as the seabed. So that is the surface of our solid Earth. And then we have a geoid model, which is simply put a mean sea level that is extended through land masses. So it's not actually exactly mean sea level, but that's a very basic definition of what the geoid is. And a lot of times I see it actually written, or I see it explained as that it's mean sea level extended through the land masses. So yeah, that definition seems to be what a lot of people use. And then you have the spheroid or the ellipsoid, which is an ellipse or a sphere that is rotated around its minor axis. And I'll explain what minor axis is once we get into the topic of spheroids into more details, and then also how to do some calculations based on the actual shape of the ellipsoid. Okay, so now we're heading more into the different types of reference coordinate systems. So even though we have ellipsoids, we have geoids, we also have two different types of reference coordinate systems. And we can refer to those now as datums as an example. So we can say that we have two different types of datum. We have a global datum and we have a local datum. Okay, so these are the two types here. We'll start with the local datum because that's the easiest one. A local datum is mainly used in terrestrial and local surveys. So in local surveys, again, we are assuming that the Earth is flat. We don't take the curvature of the Earth into account. And because of the topography in a local area, a lot of times we do use a reference coordinate systems that is well defined for that particular area. And New Zealand is a good example of that, in that we've got our own NZGD 2000 local datum. And as we progress through this course, I'll also explain how NZGD 2000 came about and how it was developed over time. Okay, so fantastic thing about the NZGD 2000 is that it's one of those datums that works very well with our global datum as well, which brings me to the next point. So a global datum is a datum that is the best fit for the entire Earth. So best fit for entire Earth, meaning that the relationship between that datum it takes the entire shape of the Earth into account, but it's also relative to the Earth's center of mass in a lot of cases. So the Earth has a center of mass. Let's try this again. Okay, so the Earth has a center of mass, and a global datum generally would use the center of the Earth, center of mass of the Earth, to define the best fit for the entire Earth. Okay, and this is what we use for satellite geodesy, because obviously our satellites are orbiting the Earth. So every so many hours, it goes around the entire Earth. So it does model the entire Earth using the center of the Earth as the reference. So for that, we call that a geocentric datum, geocentric. Okay, so global and geocentric, meaning that it's defined relative to the Earth's center of mass, and that's what's used in satellite geodesy due to the motion of the satellites. Okay, so we have a global datum and we have a local datum. And a lot of times we need to know the relationship between those two quite well to a sufficient level of accuracy because we do need to go between them. So if we are measuring using technology, if we're observing points using a specific type of technology like GNSS, GNSS is an example, so GPS is one of the examples of GNSS, but that's an example of a global datum. Okay, so that's one that takes the entire shape of the Earth, is the best fit for the entire shape of the Earth. So if we're collecting data, if we're observing data using GPS, we are working with a global datum. But let's say that we want to transfer the observations from a global datum to a local datum, such as NZGD 2000, then we might have to do transformation calculations that allow us to go between the two. So that's the reason we need to know the relationship between both the global and the local datum to a sufficient level of accuracy so that we can then transform the observations between the two datums to then output the results depending on what the end requirement for that project might be. So are you supposed to give out or present that information in NZGD 2000, or is something else like WGS 84 or GRS 80 more appropriate? So those specifications are obviously provided at the start of the project. So you do have to know that you might need to move between the two. And another thing with global reference systems as well is that the type of height observations that we obtain from global navigation satellite systems might be quite different to the type of height that we need to end up with when it comes to a local reference to mean sea level, for example.